Hey everybody, I'm Eric. So I thought I'd open this up with a bit of a story. Over Thanksgiving break, I had this really crazy idea for an application. And the thought was, what if we could write an application which counts from 0 to 100, but it does not do it by going through a loop. Instead, it writes a version of itself that prints out just one number, and then it compiles itself and increments that number by 1, and then it runs itself again. And by continuously running a more, I guess, I wouldn't say advanced version of itself, but an additional subsequent version of itself, we could count all the way up to 100 without actually having some sort of an infinite loop. The loop would be just continuously running yourself over and over and over again. So that got me thinking, and there's this idea of code that's called polymorphic code. For the beginner computer scientists or students, there's this concept of polymorphism, where you have objects that can be other types of objects based off of inheritance. That's not what this is. This is actually just writing code that changes every single time you want to run it. So I decided to give it a go and see how that turned out. So I thought it would be relatively easy at first, but then I started thinking about it and it became a little bit more complicated than I thought. So let's dive right in. So here is my application, and we'll just kind of walk through this here really quick. So here is the piece that's going to be the polymorphic piece. This is the only piece of code that we want to change, but we also need to recompile ourselves every single time that we run this application. So that means we need to know about the rest of the code in the application so that we can make a perfect copy of ourselves, minus a little bit that mutated. So if we kind of think of the steps that our code needs to take, first we need to read our own source code. Then we need to be able to modify our own source code. And then we need to be able to save our own source code. So reading our source code is pretty straightforward. All we would do is just use a little bit of file IO to read our own code file. Modifying source code is not as easy, but basically what we do is we read the source code that we read in, and then we find a very particular piece that we want to modify. Then we modify that, and we're basically doing string manipulation at this point. Then we have the modified code, and it's still in memory. And then we take that code that's in memory and we save that to disk. And we want to overwrite the version that we just used to compile ourselves. So let's go through this. So the first line right here just outputs a number, which is the incremented number. Keep in mind, this is a static or a constant value that should never, ever, ever change, right? So this is proof that if we can change this number, then we are actually doing something that changes our underlying source code. Second, we have a string that is going to point to our source code. So then here, our whole entire application pretty much just goes through the same steps, reads the source codes, modifies the source code, save the source code, then we exit. And I can actually delete that one right there, it doesn't really matter. And excuse me. Then we exit our application. So reading the source code is relatively straight easy. We have a path to the source code that we want to read, and in this case it is a hard-coded path to our source code file, which in this case is main.cpp, as you can see. And we want to store that into our source code pointer here. So this is some super simple file IO. If you haven't seen file IO before, I recommend you just read this on a CPP reference site somewhere, and that should tell you everything you need to know. So we're not going to go over this in too much detail, but essentially all this does is it reads the file that we pointed at and it puts it into memory. And this does not even know that it's source code, so it could be any kind of file actually. Next, we go to modify the code. So here's this interesting keyword, increment number, which corresponds to this piece right here. And we're pretty much looking for a needle in a haystack. So our haystack is our big block of code, that's everything. And we're looking for this piece right here. So if we find the needle, then we figure out what its position is. Then we figure out the size of the needle, which is the length of our needle, which is actually the length of this. And then we get our starting position. And then we look to see, have we reached the new line? Or have we reached the space? If yes, then we increment our start position by 1 and continue, and we keep on going until we reach a new line, because we know up here that this very last character right here is going to be a new line, so we're going to be reading this value. So we don't want to necessarily just read one character off of here, because as soon as we increment past 10, or up to 10 or beyond, then we start having 2 characters. And if we get to 100, then we have 3 characters. So what we want to do is actually read every single character until we read the new line. So that's essentially what we're doing right here. Then we take that sequence of characters and we convert that from a character string into an integer. So we're parsing the characters to understand what number it actually is. And then this is a little bit of a tricky part. We increase the number that we had, and then we have to go into our code and erase this number right here, and then replace it with the new number that we came up with. So here I just assume that our number is not going to exceed 6 digits. If it does, if we get like 1 digit shy of a million, then we have to modify this piece of code, but we're never going to get that far. This is just a demonstration. Then we set our memory to all this stuff, blah, blah, blah. Then we convert our integer to a string, and then we insert that string into our start position. And as soon as we're done, we return true. Now we have modified the code in memory, but now we need to write it back to disk. So here's a very simple block of code that just writes a file to disk, doesn't really care about what it is. So we have the path to the file that we want to create, and we take the code that we have in memory, and we are going to write an output, and here is the code section to do that. So it's relatively easy. What's interesting is that we don't actually know the length of our code. So if we made this like 20 paragraphs long or 20 pages long, we don't really care. We don't need to maintain a buffer that contains a fixed value. So that's kind of the elegant piece there. So let's give this a really quick run. You'll see that just running it once will not do anything super exciting. So it prints out the number 0 as we expected, and then it says exiting, and the program is done. We counted up to 0, but we did not continuously count. So initially, when I was trying to come up with this application, I wanted it to compile itself as well, and then I wanted it to shut down and run the new version that it compiled. Unfortunately, that doesn't really work out as you would think, because in order for you to compile a version of the program and overwrite the version that you're running, you have to actually shut down the executable that you're working on. So you can't really do that when that file is in use. It's locked by the operating system, so you can't just go in there and overwrite a file that's currently locked. It just doesn't work. So if you wanted to do that, you would need to modify the execution code in memory rather than recompiling it, and that's a whole different ballgame. But we're not interested in that. So I realized after hammering away at this that I needed to have 2 programs. The first one is this program that we just looked at, and then the second one is the one that's kind of like this manager or this launcher that continuously launches uh, a child program over and over again. So I came up with a second program, which I called Eden. And the idea was that this is kind of a garden that nurtures other programs and it can launch them and do all that stuff. But it doesn't really know anything about the programs that it's launching. All it does is gives them space to operate and run in. So I called my other program Polymorph. And if we look at, let's see, I believe it was, if we go to projects polymorph x64 debug, there's the program that we just ran. It's timestamped at 9:58. We're at 10 o'clock, so that was just made 2 minutes ago. So we can be certain that this is the program that we run. We have a literal string to it. So this was actually kind of interesting too. I learned something. If you have the capital R, this means that it's going to be interpreted as a raw stream of data. It doesn't do any kind of formatting. So that lets you have backslashes, and it does not convert these into escape characters. So normally Windows would do that. So you'd have to have like these double escape characters like this in order for this to work. Anyways, the anatomy of this program is relatively straightforward. All we do is we compile any source code given a path, and we convert it into an output file. This is going to be our executable. Then we have another function that just runs programs, and this is going to be any binary file that we give it. And then I made a little helper function that will escape a string for us. So if you have a single slash or a backslash, it's going to give you two backslashes, which makes it an escaped backslash. And if you have new lines, it'll do that. And it's a relatively trivial piece of code. So here it is right here. So we continue running until we hit a null character, and the whole time we look for these special characters and we escape them. And then if we don't find one, then we just take the string. So it's pretty straightforward. So we are just going to have a do while loop. You don't see these very often. And we are going to just run our program. And this is a hard-coded reference to the executable that we just saw in that other folder. And after this program gets run, we know that it's going to have source code that is modified, and that is this modified line right here. It's called main.cpp. In fact, we already ran it once. So as you can see right here, the number has been incremented from 0 to 1. Let's just change that back to 0. We'll save that, and we'll go back to our Eden program. And then after we compile the source code, we have an output file which matches this file right here. So what we're going to be doing is continuously outputting newly compiled executables, and that executable is going to modify its original source code until we reach 100. So it was a real pain in the ass to get the source code to actually compile. And you need to use kind of like this command line compiler. And with Visual Studio, they have this application called CL, which is their compiler that runs behind the scenes. And if I compile this program, you would see CL being run in the background, and you would see the results of that in the output log. Then there's a whole bunch of different flags that you can apply. So this is some sort of an error handling flag. This is a path to our source file. If you had more than one source file, I think you would have each of those paths listed here. Then here is where we have a output file with our E for executable. And then here we have the escape string for that. And this was not easy to find. In fact, I went to my notepad and I typed in cl.exe, and it outputs all this information, which is your command line parameters. So if you really wanted to tailor your code generation, you can just get the output and set the flags as you see appropriate. This is the main, I guess, command with all of its command line arguments that Visual Studio would run for main. Unfortunately, when you run it just in a plain old command prompt, let me show you what happens. We'll just do cmd here. If I typed in cl dot, or no, just regular old cl, it does absolutely nothing. It's not listed in the path, and the environment variables are not set up correctly. So, in theory, if you wanted to run cl.exe in a command prompt, you have to open up a Visual Studio command prompt. So once you install Visual Studio, you can go up here and click on this guy right here. And now we create a command prompt that's in Visual Studio mode. But the question is, okay, so I compile my executable, but how do I get my executable to run in Visual Studio mode with all of these Visual Studio parameters? And the long and short of the answer is that you really can't. So that was a super annoying discovery. And it makes me want to move away from using the Visual Studio compiler altogether because it's not going to work for polymorphic code. Anyway, let's just set a breakpoint right here and step into this and see exactly what happens. So we ran our excuse me, we ran our program and we saw the output. It said 0 and then it exits. And then we're about to compile our source code. So we have a couple different strings that we're concatenating together. So we have CL, we have our parameter list, and then we join those together, and we have our final result, which is CL/EHSC D blah 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 FE blah blah blah. And notice that all these characters are also escaped using my super handy escape helper. So if I were to run this, which I will, it's not going to work, and you'll see what happens. Now we just tried to compile it. We go back to our output window. It says CL is not recognized as an internal or external command. So we can't do it this way. Let's close this guy. But what we do have is our Visual Studio command prompt. And if we look at the directory here, we have CL, or I mean eden.exe. And if we just run Eden, you'll see number 0, 2, 3, 4, 5, 6, 7. And as you can see, this is now counting and compiling the same program over and over again. So this is really neat, I thought. We're counting from 0 to 100 without actually having some sort of code piece that's actually looping. You could argue that my Eden program has this loop right here, but all this is doing is running a program over and over again. The actual counting is done by the program modifying its own source code. So I thought that was pretty neat. So one of the questions could be, what are the practical applications of this? Like, this is one of those so what kind of things, right? So you could think of this in the terms of evolutionary programming. So if a program knows its own source code, it's like knowing your own DNA, and then it makes a small modification to it. And you can consider that modification to be a genetic mutation. And then it runs itself again. And if it actually compiles, then it actually was born. And if it doesn't compile, then it was a bad modification, and it can try again and try modify something else. But let's say you have like 50 different programs that are running simultaneously, and each time they're making a very small mutation or modification to themselves in their source code. And then you have them operating inside of this kind of Garden of Eden kind of thing where they all run, and after each one has run, they do kind of like this fitness evaluation thing where you say, okay, whatever program made the best mutations are going to be the ones that survive. The ones that made the worst mutations are the ones that are going to die. And the next sequence of mutations is going to happen by each program mating with all the other programs that survived and creating a new generated code output. And then we're going to evaluate the fitness of that. So you could have these programs that are kind of like mating with each other. And if you continuously have them mating with each other and creating additional generations on and on and on, you can create some sort of a program that creates subsequent generations of itself that become increasingly optimized towards solving some particular problems. So I thought that was like a really fascinating idea. And if you think about it in that context, you could say if we humans have our own source code, which is our DNA, and we can modify ourselves by having children, then our children become programs that then go on and do the same thing. In a sense, you could say that we human beings are, in a sense, programs that are doing the same thing that we just saw this code do. So, okay, big deal. What if we have programs that kind of evolve? So what? Well, the interesting thing about evolving programs is you could have them solve problems that you yourself don't necessarily know how to solve. And you may not have a model for how to even solve that. So you have to try a whole bunch of things at random and hope to get lucky. And eventually you'll kind of like move towards some sort of an optimum solution that seems very clever after several hundred generations. And I think when you don't know how to solve a problem, this might be the most interesting way of finding a solution. So, for example, we don't know how our own minds work. We don't have a very good model for intelligence. And anybody who's been working in AI has been working off of a really flawed or faulty model for intelligence. And the resulting AIs have never been smart or sentient or whatever you would call it. So if we had this kind of a system where we had these programs that are continuously self-modifying themselves, becoming a little bit more optimized, and they're trying to find the most fit version of themselves that have the most ideal model for intelligence, then we could create a whole entire series of programs that slowly become increasingly more intelligent over time. And I think that's a really exciting concept, but I haven't gotten that far yet, not even close. So this was just stage one, and it's a very rudimentary stage. And the next step would be to start creating some way of actually making intelligent modifications to our program. We don't want to just start doing random gobbledygook, because then our programs would most likely crash instead of being something of any value. So till next time, thanks. See ya.